Morning, folks. Listen, we will keep that exam on the date that it's scheduled. I'm sorry for that, but more than a majority of the class want to do it that way, and I sort of want to do it that way either. It makes your fourth exam shorter, or less material on your fourth exam. So it's good for y'all, but it is bad in that you don't get as many tests before the drop date. But if you want help thinking about that, you can come see me. I can let you know if you're thinking about dropping the class. Okay? You doing okay today? Yeah? No, it was a sleepy morning in my 7:30 class, so hopefully you aren't sleepy. Usually they're not that sleepy, remarkably, for 7:30. But let's see, let's pick up where we left off last time. Remember we had started on conservation of energy, and in conservation of energy problems, you are taking this idea that the energy doesn't change, that our initial energy is equal to our final energy, and in our initial energy we have both potential energy and kinetic energy. Sometimes one of those might go to zero, as we saw, and then our final energy also consists of potential and or kinetic energy. And then we work this problem, which you'll have one similar to it on your exam. You have one in your homework. You look at old exams, you'll have similar problems, where I have something that's traveling along a path that goes to different heights, and it'll have different speeds. And so we worked through this problem looking, we said this was our initial position, and then we said, what is the speed or the height at other positions? Here, or here, or here. Now I told you that at this point the speed was 0, and that's what we started with. We said initially, I only have kinetic energy. I don't have potential energy because I've called this point to be h equals 0. And so that has no potential energy. And then at this point, I only have potential energy because my kinetic energy has gone to 0 because the object has stopped up here. And so we went through this process where, we said that our initial energy is equal to our final energy. This was 0 because h is 0 initially. And so we have our kinetic energy is equal to our final energy, which only consists of potential energy. And then we put in the values that we have. We found that the masses cancel. I didn't really need to know the mass. And this is my speed. This is the acceleration due to gravity. And then we solve for h. Sometimes it's a little more complicated, like we had in this part right here, where we were trying to figure out what is the height or what is the speed when it goes to h over 2. And we'd already found that h was equal to 5 meters. So at h over 2, the speed, or the height rather, is 2.5 meters, or h over 2. Then we say, well, initially I only have kinetic energy. Here I have kinetic, that means at this position, h over 2, I have kinetic and potential, because it's moving and it's also at some position above the ground level. So I have kinetic and potential energy. I put in the values that I know, and then I solve for v. I found that v was equal to 7 meters per second. There was a third part of this, which I don't think we've done yet. Is that right? Yeah, Alan? All the m's cancel here. Let's start the next part C, and I'll show you how the m's cancel. We'll work it through. Now, looking at part C, the mass will always cancel. Looking at part C, which is what is the speed at point C. Well, no, let me go ahead and, Alan, let me address your question now. So my m's cancel because I have this mgh plus 1/2 mv squared equals mgh final plus 1/2 mvf squared. I can divide through both sides by m, so I can multiply this side by 1 over m. And right. It's a good point, though. I appreciate you asking. Because our masses will cancel out, and so sometimes you might encounter a problem where you don't have the mass, and it's asking you things about it. You just need to step back instead of freaking out and saying, I don't know the mass. Instead, step back and say, okay, maybe there's things that I don't really need to know in this problem. Then you'll proceed with it in this way, and you'll see what cancels out. So the mass is not relevant.
So that's
Every time that we're dealing with kinetic and gravitational potential energy, we'll work a type of problem that deals with springs, and in that case, you do have to know the mass. We'll see only with these, when we're changing h, changing height. Now, part C, we didn't work it, but we don't really need to write anything down. Because if I'm going 10 meters per second here, and I have no potential energy, over here, what is my potential energy at point C? It's 0 because I'm at the same height. So I know that the only energy that I have here is kinetic energy, and it's the same amount of energy that I had here, where it was also the only energy was just kinetic. So if I'm going 10 meters per second here, then I have to be going what speed here? 10 meters per second as well. All right? So let's work another problem. I have a video I want to show you. This video went viral on the internet some years ago. A couple of years ago. You want to know a couple of things about this. First of all, what is the woman's energy at the top of her trajectory? What is her velocity at the bottom of the trajectory right after she leaves the guy's hand? And then what is the woman's speed when she travels through the basketball hoop? So we need to assume a couple of things. Let me go down and look at something first. Yeah, okay, we're good. So assume a couple things about this, which is really all we need to know is the height that she goes up in the air and then the height of the basketball hoop. What a basketball goal is what? 10 feet. So in meters, that's roughly about 3 meters. Yeah, so we'll say that the height of this basketball hoop is 3 meters. So this distance is 3 meters. And then she goes up, I don't know, let's say that she goes up twice as high as the basketball goal. I think that's not far. So she goes up another 3 meters, giving us a total height of 6 meters. So throwing her up in the air almost 20 feet, about 20 feet up into the air. And so I want to know what is the woman's total energy at the top of her trajectory. In order to find that, I have this lady, she's here, and then she goes up, and then she comes back down again. I want to know what is the total energy here. At the top of the trajectory, she has what kind of energy? Does she have kinetic energy, or does she have potential energy, or does she have both? She only has potential energy. Because V is equal to 0, she has only potential energy. And that potential energy at the top is equal to mgh. She's pretty tiny, right? So we'll say that she's about 50 kilograms. Just making an estimate of her mass. The acceleration due to gravity is 10 meters per second squared. And then h is 6 meters. So she gets an energy of 500 times 6. That's 3,000 joules. That is the amount of energy that she has in gravitational potential. Now, right here, I want to know what is the woman's velocity at the bottom of her trajectory. This is just like the problem that we worked before, where I look at the bottom and I ask, what is the energy here? And I can compare it to some other energy, like say at the top. So let's say I'm going to compare the energy at the bottom and say that that must be equal to the energy at the top. I already know the energy at the top. Although I'm not going to put in the value here, I'll just leave that out because we'll see that that mass cancels. The energy at the bottom is only kinetic energy because h equals 0. So this energy is only mv squared, 1/2 mv squared. And the energy at the top is only mgh. Now I'm leaving out a couple of terms here because they go to 0. On this side, the initial energy, I'm leaving out the mgh because h is equal to 0. On this side, I'm leaving out the 1/2 mv squared because v at the top is equal to 0. So I'm leaving out a couple of terms here, but I'm still writing the initial energy is equal to the final energy. All right, notice that my masses, I can divide them out and get rid of them. And I'm looking for the speed, and so that v is going to be the square root of 2gh. I mean, I guess you could memorize that, but it's sort of specialized to this particular case. I would just remember the how to find the kinetic energy and then how to find the potential energy. And so that is equal to the root of 2 times 10 times 6, the square root of 120, which you know is about 11. Isn't that right? Yeah, it's about 11. Yeah, 11 meters per second. And now I want to know, what is her speed when she goes right here? Now, what is her energy when she goes right here through the basketball hoop? A number. What is the value of her energy? That's sort of a trick question. It's not 0. Think about this. Don't answer, but think about what is the value of the energy. How much energy does she have when she goes through the basketball hoop? She has 3,000 joules of energy, right? Because that energy is always the same. That's sort of a trick question, because if you think about the gravitational potential energy, somebody said 1,500. She does have 1,500 joules of potential energy because she's at half the height from where she was up top. But she has a total of 3,000 joules of energy. So I want to know, what is her speed when she travels through the hoop? Well, I can do it in a similar way like we did before. I can say the energy at the bottom, or you could say the energy at the top, either one, is equal to the energy at the hoop. And I know those are going to be constant. She'll always have the same amount of energy. She'll always have 3,000 joules of energy. It'll just be proportioned differently between kinetic and potential energy. So energy at the bottom is 1/2 m times 11 squared, because that was the speed that I found here, equals to 1/2 m, I'll call this v hoop squared, plus m times g, and I'll go and put in the value here of 3 meters. Notice my meters, they all cancel out. And then I solve for v hoop. To do so, I say 1/2 of 11 squared, which is, I'm going to go ahead and, I know 11 squared isn't really 120, but I'm going to go ahead and write it as 120. Minus g times 3, that's minus 30. So I took this term, subtracted it from both sides, and took it over here. Divided by 1/2, dividing through by this term, and then taking the square root of all of that gives me v hoop. So I combined several steps there, algebra steps. I subtracted 30 from both sides to bring this term over. I divided by 1/2 to get rid of this term, and then I took the square root to get rid of this squared sign. So 3 different sort of algebra steps that I combined all into one. So that's 60 minus 30, 30 over 1/2. It's going to be the square root of 60. What is that? What is it now? Okay, we'll just call it about 8 meters per second. Okay? Is that right? Yeah. Very similar to the bead problem, or the object on the roller coaster problem. Yeah, China? The 30 comes from right here. G is 10, 3 is times 10 is 30.
Couldn't you also cancel out the 2 left-hand side?
No, you can't do that, because if I multiply this times 2, it would get rid of this half. But if I multiply this whole thing by 2, I get rid of this half, but then I have a factor of 2 here. So when you're adding things, you can't just get rid of one term. You follow? And you have to do it to both parts of the sum. Okay? I know it'd be nice to get rid of that half. And I remember when I was first learning this, I thought, gosh, I can just cancel out those halves, but you can't do that. Not when you have the gravitational potential energy involved. Okay? All right. I think I might have one more practice problem like this. Okay, this is a similar problem. You know, we've done this from before with kinematics. And by the way, before we get into this, I just want to show you that now we do have an equation sheet. It's on the website. So for the next exam, you'll have this equation sheet. Just because we're getting more equations, we're sort of getting more involved. So here's the work, here's the kinetic energy, here's gravitational potential energy, this is conservation of energy law, and then some other things that we'll get into. If you have the workbook, it's the very last page. I think it is. It is the very last page in the workbook. So what I recommend is that you keep that in front of you as you're working through the homework, as you're practicing the old exam. You know, paste it up on your bathroom mirror or somewhere else that you look. Not that you're trying to memorize them, but just that you know what's on there. So when you come to an exam, you know what's on the equation sheet and what's available to you. All the equations, I'm pretty sure, are on there, but you know, some things like your trig functions and stuff like that you might need to know, that's not on there. But that's what you'll have on the next exam, the final, and everything else. All right, let's try this quick test. Just to remind you, our procedure before would have been, I know the initial velocity, I know the acceleration, I can find the time, and then if I can find the time, I can find the y height to which it goes up to. If you want to work it that way, that's fine, but it's easier to think about the energy and how the energy changes. All right, we'll wrap this up in another 15 or seconds or so. Feel free to ask your neighbor. I'm going to stop at 310, all the way to 312, 312. Okay, good. I'm pretty sure B is right. Well, let's take a look. So this is just like the cheerleader problem, right? It's really like, it's just like all the others too. I have an initial velocity equal to 15 meters per second. It goes up to some height and then comes back down again. I know up at the top that the velocity is equal to 0, or the speed is 0. So I know that it only has potential energy. At the bottom, h is equal to 0, so it only has kinetic energy. So we say the energy initial equals the energy final. That's the kinetic energy equals the potential energy in the initial and final states. This is going to be 1/2 m times 15 squared equals m times g times h. The m's cancel, so it's going to be h is 15 squared over 2, that's 1/2 of 15 squared, times 10. Is that 11.5? It is? Oh, okay. I was probably using 9.8, but we'll call it 11. But D is the right answer there. Yeah, if I was using 9.8, it'd make the value come out a little bit bigger. I would expect a couple problems like this on the test. At least, yeah, a couple problems like this on the test, where I'm asking you the speed or the height at particular points. There's a homework problem like it. There's every test you ever find. We have questions like this. Let's do a few more clicker questions before we move on to Hooke's law. We did up to 5 point what? 15. Huh? 14? He was just trying to get me to go ahead so they could see the answer, right? Oh. This one? Oh shoot, no, I'm sorry, we're not ready for this one then. Sorry. Yeah. Sorry guys, let's go back. So let's look at elastic potential energy and Hooke's law. You guys have probably seen Hooke's law. You might have studied it in chemistry because sometimes Hooke's law is used to model the bonds between atoms or molecules, because sometimes those atoms or molecules will vibrate, and we'll often use Hooke's law to describe how they vibrate because they act in a similar way. But Hooke's law says that the force from a spring is proportional to the displacement or compression of the spring. Or I'll say compression, elongation of the spring. Displacement is the same as either compression or elongation. It would just change the sign whether you're compressing it or you're stretching the spring out. Hooke's law is written like this. It says that F is equal to negative K times X. The force F is in newtons, X is in meters, and then K is a spring constant. It's a constant value. It's in newtons per meter. So this value is a constant. It's determined experimentally. You guys determined it, or no, you didn't. We'll have a lab, I think, where we determine the spring constant of a spring. You just measure F, you measure X, and then you can calculate what K is. It's a constant. It's in newtons per meter. Notice how the force, I have this figure, here's our spring right here. These are all the forces that we have acting on this spring. In this particular scenario, it's moving to the left, and so the spring is pulling in that direction. Kinetic friction is this direction because it's opposing the direction of the motion. We have our normal force straight up and our weight straight down. This is our equilibrium position. The spring, when it's at rest, will be at this equilibrium position. So in this case, I have stretched the spring in this way. So I've given it what kind of displacement? Have I given it positive or negative displacement? I've given it positive because I call my equilibrium point 0, and anywhere to the right of that equilibrium point will be positive. So here, if I push the spring out this way, that's in a positive direction. So my equilibrium point is centered around my coordinate system. My coordinate system is like that. So now when I stretch the spring out to this distance, this is a positive x value. It's positive x because I'm to the right of the equilibrium point. Right? Notice how the force of the spring is always opposite the displacement. In fact, that's why we have this negative in Hooke's law that describes the force and the displacement, because the force of the spring will always be opposite the displacement. You can think of it as like the spring wants to get back to that equilibrium position. The spring doesn't really want anything, right? It's just a spring. But it feels a force that would pull it back towards this equilibrium position. Likewise, if I push this thing back in the negative direction, the force of the spring would be towards the equilibrium position. So Fs will always be towards the equilibrium position. So the spring wants to return to its equilibrium position, which is at x equals 0. You know, as you encounter these problems, just take a look at the scenario and think about it. and you'll be able to reason out what is the direction of the spring. Because you sort of have an intuitive sense about springs, and I think it's correct mostly. That is that the force of the spring will always be towards the equilibrium position. If I pull a spring away from its equilibrium position, it'll go back towards that equilibrium position. Now, we really do that just to talk about conservation of energy. If I have a spring, and I have some mass over here that I'm pushing, and I compress the spring to a certain displacement, the elastic potential energy, I've written it here, let's write it again. The potential energy of the spring is equal to 1/2 kx squared. And so at this point, I have elastic potential energy, but since it's not moving, I have no kinetic energy. I press this block, I compress the spring, and give it elastic potential energy. Then, if you let it go, the object comes out here, your spring stops here, and your object keeps coming on. Like, you know, my son likes to take rubber bands and shoot like spit wads and stuff at my daughter. Do you ever do that? You're going to spitballs or whatever. He likes to shoot things at my daughter for whatever reason. And sometimes she does it to him too. She's starting to figure out that she can. But it's a similar thing as this, that you're converting elastic potential energy, PE, into kinetic energy. Now we can derive this elastic potential energy. It's not a terribly difficult derivation, so I'm just going to do it for you. You're not responsible to know it, but if it helps you understand better, that's great. The potential energy is equal to the negative of the work. If I do work on an object, I change its potential energy by that amount, but negated. This is equal to the integral of negative f dx. That is, I'm applying a force over certain distances, and I add up the product of f and x. If this doesn't make sense to you, don't worry about it. But some of you are in, actually none of you are in integral calculus, are you? Some of you have had it. So if I integrate over this f dx, I get the total amount of work done. That f is equal to negative kx. That's from Hooke's law. The integral of that with respect to dx is 1/2 kx squared. So this is where I get the elastic potential energy of a spring. It's from integrating the work done on a spring and then putting in this negative kx. Again, you're not going to see that on the test at all, so don't sweat it, but just a little sidetrack, a little side visit into integral calculus. All right, let's look at some problems. Okay, so here I have a block of mass 1 kilogram. It's attached to a spring. Spring constant is 1200, and the spring is compressed by 20 centimeters. So somewhere a hand has come in and pressed this thing in to 20 centimeters from its equilibrium position. What is the velocity of the block when it passes through the equilibrium position of the spring? It's going to work out very similarly to what you did before. You're going to take only potential energy here, only kinetic energy here, and you know that those two energies will be the same. And you want to solve then for what is the speed of the block at that equilibrium position. If you finish this one right away, I'm going to have a second question. It's not going to be a clicker question, but we're going to consider what is the speed at 10 centimeters from the equilibrium position. If you want to start thinking about that, you can. At 10 centimeters. All right, let's do about 10 more seconds. I'll stop at 3 minutes. Guess if you're not sure. 3 minutes, just a few more seconds. Okay, looks like B is the most popular answer. I think that's right. So what we're doing here is we have potential energy here, and then we only have kinetic energy here. I only have kinetic energy here because x equals 0, so the potential energy goes to 0. So we'll say potential energy initial equals kinetic energy final. Remember, I'm also imagining that I've also written kinetic energy initial give me just a second. I'm also imagining that I write kinetic energy initial here and potential energy final here. And in fact, I do think about those things, but then I realize, oh, well, the kinetic energy at this point is 0, and the potential energy at this point is 0. Kinetic energy is 0 because V equals 0. Potential energy is 0 because X equals 0. The position, it's at its equilibrium position. So then I say 1/2 kx squared equals 1/2 mv squared. Now in this case I can get rid of those halves because there are no other terms. I can just divide through by half or multiply by 2. I can't cancel the mass. I need to know the mass, but now I want to solve for v. So I say v is kx squared over m and the square root of that. I have to be careful of this because X has to be converted into meters. You have to convert everything to SI units. So K is 1200 newtons per meter. X is 0.2 meters. And then M is 1 kilogram. See, that's the square root of 240, right? Is that right? Oh, 0.2 squared. So this has to be squared because it's kx squared. And then the right answer is B. It's not the square root of 240. It's square root of something else. I don't know what it is. 48, square root of 48. Okay, which is 6.9. Okay, let's look at a different problem that's similar but just a little bit different, where I want to know now what is the velocity at 10 centimeters. What is the velocity at this point right here? And in that case, I'll just sort of do it down here. I have kinetic energy, or excuse me, potential energy initial is equal to potential energy at 10 centimeters plus kinetic energy at 10 centimeters. So this problem is different because when the spring is fully compressed, I only have potential energy. But when I'm at 10 centimeters, I have both potential energy and I have kinetic energy. So, notice the parallels here with our roller coaster problem. This is sort of like when it's an h over 2. It has both kinetic and it has potential. The only difference is, instead of mgh, I'm doing 1/2 kx squared. So I have 1/2 kx squared. I'm going to go ahead and put in the values here for x. That was 0.2 meters squared equals 1/2 k 0.1 meters squared plus 1/2 of 1 kilogram times v squared. And then I solve for v. K was 1200. So 600 times 0.2 squared is 24. 600 times 0.1 squared 36 plus 1/2 v squared. And then this is 18 times 2 equals v squared. I subtracted 6 from both sides, multiplied both sides by 2. Square root of 36, which is equal to 6 meters per second, which is equal to v. You could see a problem like that as well, and you'll see some in the old test as you look back. So for conservation of energy, we have a couple of different problems. Both are dealing with kinetic and potential energy, but the only difference is that sometimes that potential might be elastic potential energy, and sometimes it might be gravitational potential energy. One last thing in this chapter is power. That's not good. I think this is the last thing. Yep. You're not going to see a whole lot of power on the exam, but you'll probably see one question that'll just require you to do a simple calculation or just to define what power is. I have a friend named Power, actually. Isn't that funny? Like his name is Power. All right. He's sort of had this rough week because like his supervisor has been making him work overtime. Because power is work overtime. Do you get it? The power is work overtime. I see some of you thought that there might have been a joke there, but you weren't sure. Like maybe he really does have a friend named Power, right? But power is work over time. It is the power at which rate or at which energy is transferred or work is done. The unit of power is, what is the unit of power? That's the watt. All right, it's the watt. Horsepower is another unit of power, but we use the watt. 1 watt is capitalized because this person's name is 1 joule per second. You know, also be able to find the basic SI units of the watts. If it's work over time, you should be able to do that. It's going to be force times displacement over time. And so the basic SI units is going to be a kilogram meter per second squared, that's force, times distance over time, so this second squared becomes a seconds cubed. Those are the basic SI units. Don't memorize them, but be prepared to produce them to figure out what they are. But by no means should you memorize them. Just remember the formula. Actually, the formula is on the equation sheet. Just remember how to put in the basic SI units for each of those variables. Let me write this down. I've never asked students about this. I'm not going to ask you about this, but you could see it maybe on other things like the MCAT or whatever it is that you're taking. But because power is equal to this force times distance over time, notice here that I have this distance over time embedded within this. I can also find the power done by a force as F times V. So if you're concerned about that, then there it is. Okay? Let's wrap up the clicker questions for this chapter, and then we'll put this baby to bed. How does the work required to stretch a spring 2 centimeters compare to the work required to stretch it 1 centimeter? How much work is required to stretch it? How much more work is required to stretch it 2 instead of 1 centimeter? All right, we'll stop at 50. Stop at 50. Okay, C is the right answer. Remember our work causes a change in energy. So when I do work on a spring, I change its potential energy. When I compress a spring, I change its potential energy. And that potential energy is 1/2 kx squared. If I double this amount, which is what I've done, I have 1 centimeter or 2 centimeters. They're different by a factor of 2. Multiplicate a factor of 2. So if I multiply this times 2x, because it's squared, I get a factor of 4 over here. If I have a factor of 2 right here, it's squared, I get a factor of 4 over here. A mass attached to a vertical spring causes the spring to stretch and the mass to move downwards. What can you say about the spring's potential energy and the gravitational potential energy of the mass? That's what my spring is doing. What happens to the energies of the mass and the spring? All right, let's stop at 110, 110. Just a few more seconds. Okay, let's see. C or B rather is the right answer. Now I'm asking about a couple of things. I'm asking about the potential energy of the spring, which is right here, the energy that's all wrapped up in that spring, and then the gravitational potential energy of the block. So the block is moving from one position to a lower position. When I move to a lower position, I'm decreasing H. That means that I'm decreasing PEG. So the potential energy of the spring, the gravitational potential energy is decreasing. So that leaves only A or B. All these others have PEG increasing. And the potential energy of the spring, because I'm stretching it out more, it's going to have more energy wrapped up in that spring. So the answer here is the spring increases, the gravitational potential energy decreases. Three balls of equal mass start from rest and roll down different ramps. All have the same height. Which has more speed at the bottom of the ramp? Let 1, 2, 3 be A, B, C, or is it D, which is the same? I want to know which has the greater speed at the bottom of the ramp. We're assuming frictionless. All right, I'm going to stop at 105. 105. Okay, awesome. D is right. They're going to have the same speed because they all start at the same height. They all start at the same height, so they all have the same gravitational potential energy. When they get to the bottom, they're going to have the same kinetic energy because all that gravitational potential energy will convert into kinetic energy. Let me ask you another question. Which of them will have the greater speed at the bottom of the ramp if friction is relevant? So the same question, but we're just saying you have a frictional force that is acting on the balls as they go down down the ramp. Which one will have the greater speed? If friction is relevant, ABC, or do they still have the same speed? Okay, doing really well. I'm going to stop at 40 seconds. 40. Okay, good. A is right. That's awesome, because you know what? Friction is a non-conservative force. When friction acts, you lose energy. Friction is also path dependent. So the longer the path, the more energy you lose. It is dependent upon the path that you take. So in this one, you lose more energy as you go down. Or excuse me, you lose less energy because you're acting over a shorter distance. You can think of it too that the work done by the frictional force is F times D. So since D is shorter here, you lose less energy. Friction does less work. Hey, do y'all know what Mozart is doing right now? Decomposing. Okay, have time for a couple more. The truck initially at rest rolls down a frictionless hill and attains a speed of 20 meters per second at the bottom. What if you want them to go twice as fast? How many times higher must the hill be? If you want V to increase by a factor of 2, by how much do you have to increase the hill? All right, let's stop at 105. These are tricky, but you'll probably have some like this on the test. So E is right. At the top, he has mgh. That's his energy. At the bottom, he only has 1/2 mv squared. I want to increase V by a factor of 2. I want to go from 20 meters per second to 40 meters per second. But if I increase that by a factor of 2, I have to increase this by a factor of 4, because I have this squared term right here. If I double V, I have to quadruple H. So you have to start them at 4 times the original height in order to get them to go twice as fast on the bottom. The box is sliding on a frictionless flat surface, runs into a fixed spring, compresses a distance x to stop the box. If you double the initial speed, how much will the spring compress in this case? So I make it go twice as fast. By how much more is it going to compress the spring? By what factor? Stop at 55, 55, 55. Okay, good. D is right. So I have 1/2 mv squared. That's the kinetic energy in the beginning. At the end, he only has elastic potential energy, 1/2 kx squared. If I double the speed over here, I'm also going to double. Because they're both squared, if I double this one, then I'll also double this one. That'll give me a factor of 4 on both sides. I'm going to keep the equation balanced. Listen, we're almost done with chapter 5, so you should be looking at the homework, going through the old exams, picking out those questions that deal with work and energy, and be preparing for the exam, which is coming up in a couple weeks. Okay, y'all have a great day. I'll see you Friday.